Good afternoon, everyone. Thank you. So I'm going to spend a little bit of time just talking about who I am. One sec. So my name is Candice Scarborough. I am a director at Parsons in the cyber and national operations. My career over the years has taken a lot of turns. Originally, software engineering background. I spent some time working in the commercial sector at one of the largest banks in the world. And so a lot of my time spent with homomorphic encryption, it actually comes from the banking industry and some of the things that we were trying to prove out and understand. I believe that, there's a lot of applicable use cases now that I'm back on the defense side of the house. But adoption, standardization, things like that are going to take a little bit more time. So homomorphic encryption, which is the subject of today, is not something that's new, but a lot of people don't know much about it just based on complexity, compute, and all of the things that need to come together in order to use it, right? There's a barrier to entry. And so not a new technology, but people don't typically know as much about it. All right, so agenda for today is we're gonna understand side channel attacks. I think that's important for a level setting for folks to understand, why would we spend all of this time and energy to go the homomorphic encryption route? What is homomorphic encryption gonna provide us as it relates to side channel attacks? And then we'll talk about limitations, and we'll end with a slight demo of an application that I created that just shows the basic usage. All right, so this is the video. One sec, trying to get it to play. There we go. So imagine it's the year 2030 and a major election is underway. Citizens across the country are casting their votes from the comfort of their own homes, using their favorite devices, so their smartphones or their tablets. The election is crucial and every vote is going to matter. But here's the twist. Instead of traditional voting systems where votes have the ability to be intercepted or tampered with, we're now using this revolutionary technology of homomorphic encryption. Homomorphic encryption enables us to protect the privacy of our data by taking the votes as they come in and encrypting them. And then we're able to do all of the counting that needs to happen for the election system without ever decrypting the data. So imagine a world where expats, deployed military, or even people that are traveling have the ability to securely submit their votes without the issue of compromise or potential tampering. Imagine that ability and that flexibility. Now that's a gross oversimplification of all of the things that need to come into play, but homomorphic encryption is going to be a key tool in that technology, and there's actually research underway to be able to do this and implement this in the future. Oh man, we're still here. Hold on one second. All right, so side channel attacks. Not a lot of people, have experience with kind of preventing or understanding side channel attacks, so I'm gonna level set that here. Side channel attacks are gonna be exploits or information leaks that focus on vulnerabilities within physical hardware or being able to siphon out information based on observing the physical characteristics of a lot of times what'll be like virtual machines or cloud computing environments. It's gonna be different than exploiting the network protocols or the things that we traditionally see with software exploitations. So I'm gonna walk through an example of a probe and timing side channel attack and exactly how that works. If you are on, in this example, a multi-tenant VM. So you have a multi-tenant VM where both the victim VM and the attacker VM are both legitimate users of that multi-tenant, right? So the way that the prime and probe technique starts is that the attacker VM is going to begin trying to fill the shared CPU cache with its own data. So in this space, here we go. This is done by trying to execute the same set of cache instructions over and over. And the goal is for the attacker VM, right here in this example, we see a few hits on the shared cache, but the real goal is for him to try to cover the entire space of the shared cache to be able to kind of prime the entire system. So next step is that the attacker, he's primed it, he's put all of his malicious lines of code and things that represent his viewpoint in terms of the shared cache in, and he's gonna let the victim process execute, right? The victim process is gonna come in and it's going to perform whatever operation, some sensitive, some not sensitive. And as that is happening, once the victim starts to access the shared cache, there will begin the eviction process. So here, as you can see, the red is where the victim process had executed cache lines. Now the victim's processes are running and they're taking over and evicting the attacker's lines of code. So next up, we have to probe for timing. So again, the victim's process has done its thing. The attacker VM is going to try and execute the same lines of code, the same cache instructions that were previously done when we began the probing step, or the priming step, I'm sorry. And so after that continuously happens, the attacker VM is trying to understand whether or not that particular address in cache has actually been evicted and the victim's information has taken the attacker's cache instructions out of the shared memory or out of the shared cache. What that tells you about the data is that when you're measuring timing, the attacker now understands if it's been evicted, if the victim's code has evicted its own code, that is where the victim has executed on the cache, so they're able to understand where that victim's processes are living. This happens continually over and over, and by measuring the time it takes to access the cache lines, the attacker can infer certain things about what the victim's process is doing. This will continue to happen, and they'll continue to analyze the data to determine if there's something that is happening in a way where it's probably cryptographic operations or plain text operations. The longer it takes for eviction to happen, it means that there is something that's sensitive happening in that space as it relates to cryptographic operations, and the attacker can kind of start to infer certain activities that are being executed by the victim's data. Questions? Just making sure people are following. Okay, good. All right, so homomorphic encryption is a form of encryption that allows computations to be performed on ciphertexts without needing to decrypt the data. The results of these operations, when decrypted, will match the results as if these operations have been performed on the unencrypted data. So here's an example of a traditional cloud storage and computation model. The first thing that happens in this space is that you have the plain text data coming in, it's encrypted, and then we have the resulting encrypted data. When we are outsourcing information across privacy barrier lines, so maybe you're sending your data out for a cloud service provider to do some type of manipulation on the data, some type of computation, at that point, it's no longer within your realm of influence or within your sphere to control. And so you're sending the encrypted data over the privacy barrier. And at that point, in order for a cloud service provider or the computation provider to work with your data, they're going to have to decrypt that data. So this is the traditional model, right? You're going to perform some computations, that service provider will provide some type of operation on the data, and then they'll encrypt that data again and send it back across the privacy barrier. So obviously there's issues with this. The cloud providers must have unencrypted access to the data, which leaves your information vulnerable. And customers must trust that whatever cloud provider or the service provider is protecting your data the way that it should be protected. You really rely on the policies and practices of that particular entity that's over your privacy barrier. So how does this change when we have homomorphic encryption? Homomorphic encryption, the process is going to start out exactly the same. You're going to have the plain text data. You're going to encrypt that data. That data is going to go across the privacy barrier. But instead of having to decrypt the data so that you can perform computations, homomorphic encryption allows you to perform basic operations on that data without having to decrypt it again. So this is the process here. It's very much simplified, and it allows for the computations to be performed directly on the data. This ensures data privacy and also keeps exposure relatively low in terms of if that data is actually compromised, it's compromised in its encrypted form, and so there's nothing that the attacker can gain from accessing that encrypted data. So overall, there's a lot of great implications with homomorphic encryption, right? Obviously, the one that I just mentioned is that if someone gets access to that data, that data is pulled back, it's still in its encrypted form. There's nothing that the attacker can do with that information. It's useless to them at that point. It's in a space where they can't use it. But the other thing that's interesting about homomorphic encryption is that we are talking about side channel attacks in this particular instance, and side channel attacks are going to look at things like timing, power consumption, and electromagnetic emissions. And so what happens with homomorphic encryption is that it makes the data uniform. When it's encrypting things into a ciphertext, you're now doing operations on ciphertexted data. And so that doesn't leave the same type of physical characteristics that can be observed. It's not going to create increased timing when something's processing the homomorphic data. It's not going to have increased bandwidth in terms of computational bandwidths that can be observed. So it creates uniformity in processing of that data. And then also it limits the idea of key exposure. You're not decrypting the data, so there's no way that you're going to be sending that encrypted key throughout your ecosystem so that it could potentially be obfuscated and taken out or observed. So there's multiple types of homomorphic encryption. They all have varying merits, right? As with anything else in this space, things that are required in terms of processing power and storage are going to be some of the triggers that we pull when we decide which type of homomorphic encryption that we are going to choose. There's 3 types, and they all have varying schemes that have been created to try and withstand each of these types of limitations. So partially homomorphic encryption supports either addition or multiplication on encrypted data, but not both. And it's suitable for encrypting things that are going to only require a limited number of operations. There's multiple schemes that have been designed. Some of the most common ones are going to be Pallier or L-Gamma, if you guys have heard some of these schemes. Somewhat more homomorphic encryption is going to be supporting a limited number of both addition and multiplication operations. A lot of times these particular schemes are used when you have machine learning use cases that you want to use with homomorphic encryption. So machine learning use cases will require us to do a lot of training of data, and so that might require us to do multiple operations. And then lastly, fully homomorphic encryption. It supports an unlimited number of multiplication and addition operations. It's maximum flexibility, but it also creates the largest size ciphertext, which means that you'll have to have more storage capability and more processing capability in order to maximize the effect of going all the way to fully homomorphic encryption. So how do you choose, right? It really is going to depend on your use case. Do you need to be able to support multiple operations? Are you doing something that only will need one type of operation? So in the case of an addition or a multiplication, it will lead you to choose something that's a little bit easier to implement and less computation power is required. So it's really about the data that you're trying to protect when you make this decision. If you're going the fully homomorphic encryption route, again, you have to understand that you're going to need a lot of storage space and you're going to need a lot of processing power. And so a lot of times, depending on what operations you need to do on the data, people tend to gravitate towards partial or somewhat homomorphic encryption as it requires less resources in order to be successful. So limitations, right? We've already talked about some of these. The high computational overhead is going to be number one, right? You have to have a lot of processing speed and a lot of processing power in order to do operations on homomorphic encrypted values, especially if these values are going to be large data sets. The large ciphertext size, as we discussed already, is going to require you to have a lot of storage ability. And so, sometimes that's just one of those things, especially in a VM environment. When we're asking for more storage, that's creating more expense. So that's something that's also tends to be a limitation. As I said, I came from a banking environment, and so it was extensively expensive to try and implement homomorphic encryption across all of the data sets. So we had to pick and choose exactly what was going to be the biggest, bang for your buck. What type of data is the most sensitive that you would want to invest supporting in a fully homomorphic encryption scheme against? Energy consumption, we've discussed that. We just need a lot of processing power. These are very large ciphertexts. If you're going the fully homomorphic encryption route, if you have lots of data, like the machine learning use case where you're trying to train a model with large data sets, it's going to require a lot of energy consumption. But the last one is a little bit less well-known or understood in terms of standardization. I know when I began my journey of trying to understand which homomorphic encryption schemes we were going to look at, there's a ton out there. They all have a lot of trade-offs and a lot of, pros and cons. And so understanding the schemes and the underlying cryptography is going to be really important to understand what is going to be good for your particular use case. And so there's not a lot of standards out there. If you're working with a Python data set, there's a ton of libraries that are wrapped around Python, libraries that you can use. There's Microsoft Seal. There's a ton that are out there and they all have their own merits, but there's no requirement for standardization or compliance. So when you're trying to build an ecosystem and you want to integrate with other components, you have to be very careful about which schemes you choose, things being open source, right? Having vulnerabilities. And so we really need to get to a place where the industry is going to look at standardizing a lot of this in order to make it really valuable for industries to adopt. So there's a lot of industries that could benefit from the adoption of homomorphic encryption. Obviously, banking is one where I feel like they're making great strides in those data sets, health insurance, but there's also opportunities for government and defense. If we need to protect classified information, also in machine learning environments where we're trying to train models, especially in the defense industry, that could be really valuable. And then also, we just need to make sure that we are securing systems appropriately in these industries. Cloud computing is obviously another area where there could be more adoption of homomorphic encryption, right? We are trying to protect all the privacy boundaries of our users, of our tenants, especially in multi-tenant cloud VMs where side channel attacks are common and are easily executed. And lastly, telecommunications. Privacy preserving customer data analytics. There's a lot of information that we can extract from telecommunications, but how do we make sure that we ensure the privacy of the customers that are networks that are sharing that data and that information? How do we make contact tracing and health data processing more secure? Awesome. So I'm going to switch this over very quickly to a little partially homomorphic encryption demo that I created. It is a Python server script. It's wrapped using LightPHE, which is a pretty common Python library that's used for partially homomorphic encryption. As I said, there were a lot out there to choose. Microsoft Seal is another pretty well-known and well-established homomorphic encryption library. And so I just, had to make a decision for today because I wanted to show you guys something very quick and interesting. All right, so for this particular demo, I do want somebody to come up. Oh, sorry. So I'm gonna ask someone to come up and be a volunteer for me. I just wanna prove here that I don't know the numbers that are actually gonna be input into this tool, and we wanna make sure that we see it work. If I don't have a volunteer, I'll make my husband come back up and do it. All right, we got a volunteer? All right, I saw somebody raise their hand. Sailor hat? Okay, come on up. All right, it's very, very simple. All I need is 2 integers. Okay. And preferably 2 integers that we can add in our head because I've seen people put in crazy numbers and then I gotta do the math, so.
Okay.
I don't wanna do all that. So just any 2 integers, you could enter them in there. I'm not looking.
You're not looking?
No, and nobody else will know what you entered. So you have to remember what you entered too.
Absolutely. All right. Oh, hold on. I screwed up already. Okay.
All right. You remember what your 2 integers are. All right. So we're going to go ahead and calculate the sum for these. But the point of this demo, right, and I can show you guys code later afterwards if you want to look at it, is that it's going to read in the values. It's going to generate the ciphertext. And what we're trying to prove here is that the ciphertext that got generated for the first integer, the ciphertext that got generated for the second integer, should equal the ciphertext that got generated for the sum, and then what that decrypted result should be. So I feel like if your numbers, were they gonna add up to 39? Is that the right number? Okay, perfect. All right, so here's what the ciphertext looks like for a simple integer. In this particular homomorphic encryption demo, like I said, it's LightPHE, but we're using Palier, so we could have done multiplication or addition. In this case, we are doing addition. So I'm gonna go ahead and show everybody the decrypted value. Is that your first integer? Yes. So 28 was your first integer, great. And then we're gonna go to this ciphertext. Again, really large ciphertext for a simple integer. So if you guys can imagine, if you had, billions of pieces of data or large numbers, how large the ciphertext might end up being. But that value, we decrypted at 11. That was your number. Okay, I'm excited. So here's the ciphertext. So in this particular demo, we went ahead and added the encrypted values. We did not have to decrypt this data in order to generate this ciphertext. So I wanted to prove to people that the ciphertext is here. This is what it looks like. And when we decrypt that, your number is 39. Awesome. Thank you. So one of the other things that you can do with this particular demo is using the same values, his same numbers. What we want to guarantee is that if I put in the same 2 integers a second time, that a different ciphertext gets generated. It would not be a very secure encryption paradigm if you generate the same ciphertext each time. So I'll do that on the screen. I won't make him come back up and do that for us, but I got to remember what the integers are. It was 28 and 11. So we'll do 28 and we'll do 11. So we still have the 39, so that's great. First step, it looks good. And then we'll compare the ciphertext. So this was the original ciphertext. The best way for me to compare these two, I didn't write like a diff tool in the script. It would have been too much. So we can see the last 5 digits, right, are 11, 45, 1. We can look again and say that's still, 28. That's what we generated before. And you can see here, this ciphertext has the last 5 digits are different. So we're looking at, 36810. but the value's still 28. So that's just a little bit of a cute little proof of concept. I wanted to do something that was quick. It took me, less than an hour or so to write this server script. There's also some logs that you can look at that shows as you're manipulating the data that you can compare the ciphertext to make sure that it's what we're expecting it to be. But I just wanted to show proof of concept, what it looks like, taking basic integer numbers, doing the encryption, and then doing the mathematic operations on the encrypted data. So at this point, that is the end of today's presentation. I'm going to open the floor for questions. Before I do open the floor for questions, I just want people to know that I'm not a crypto expert. So if you're going to ask me anything about the mathematics behind all of the different crypto schemes and all of that, the encryption schemes, I probably won't have those answers. I am sure there are people in this audience, though, that are experts, so I will turn it over to any of them if they can answer it. So, questions? Oh, yes, sir.
Can you hear me? Thanks so much for the presentation. So it covers confidentiality. Are there any schemes that also provide integrity? So it's great that we can calculate on our encrypted values.
Right.
How do I know that the end encrypted value is the one that I put in? Say for the case of voting.
Right. So there are abilities to create signatures on homomorphic encryptions. They're similar to like how we would do like checksums on the data, but that's an extra step, right? To generate signatures to verify, is this the original ciphertext that I generated and that I'm receiving back? How do I guarantee that this is coming from who I expect it to come from in terms of the computation that occurred on it? So there is the ability to apply signatures to homomorphic encrypted ciphertext. If that does that answer, that answers one side of it, I think, right? But did that answer the question for you? Okay. All right. And if there's someone else in the room that has a better answer, I would love to hear it. Okay. Any other questions from the group?
Yeah, I was wondering if there's any history to it. Like if you add a number and then you get a decrypted text or you get the encrypted, can you go backwards to see where you've come from?
I don't believe so, because at that point, the ciphertext is permanently changed. So there's no like data provenance that follows the ciphertext. There's not like metadata associated with it. Question back there, I think, yeah.
So you had demonstrated that for the same input, two different ciphertexts would be generated. What randomness mechanism is used to accomplish that?
So some of them are different. It all depends on the schema that you choose. Right now, I think I can think of like 9 or 10 schemas. They all have like really crazy names off the top of my head. So like L Gamma was one that we mentioned earlier, and Palier is another very common one. There's BGV, there's several of them, but they will have different ways that they're implementing the underlying mathematics. Some of it is going to be based on timing, right? Like epoch times and things like that for the randomization that occurs. But I would say, like, if you want to learn more about how each of them implement it, definitely look them up. Off the top of my head, that's the main one in terms of deciding things based on epoch time. Are we done? I think that was any more questions? Okay, one more question.
So if the CPU itself that does the calculation is compromised somehow, how does the final numeric result get shown that it wasn't manipulated to, even though it produces a final ciphertext that should be, how is the chain between the three results show that there was no computational manipulation?
So you would have to, like I said earlier, create a homomorphic signature. Like the homomorphic signature kind of pairs along with the ciphertexted data, but that's an extra step, right? So in this little version that I created here, there's no way to determine that it hasn't been tampered or modified in that space. So you'd have to attach a signature with it. And there's a lot of different ways to achieve that. But the easiest one is going to be to generate the homomorphic signature alongside that ciphertext before it's transitioned across the privacy barrier.
So I had a question. This might come as like a naive question, but so your example was with integers, right? So if you did it with strings, could it do like concatenation, or is that a different?
So they have the ability, some of the libraries or some of the schemas, let me rephrase that, have the ability to do anding or oring, right? So you could figure out a way to do the operations together to concatenate that data using ors and ands, right? It's not really concatenating the string, but it's representing that same basis. And I think on the end, you'd be able to get the same values out of it.
Okay, thank you.
I think so. I think that was the last question. No more questions? All right. Thank you. All right.